happy to introduce the last speaker of this morning and therefore today, who is Mark Hamilton. He'll be speaking on the independence of polarization for Lagrangian fibrations in integral affine geometry.
Thank you. Is this on? Can you hear me? Okay. Thank you for, I'm humbled to be speaking in the presence of such luminaries, but I'm delighted. Thank you for the opportunity to speak. And happy birthday to Ellen, Lisa, and Jonathan. I was the PhD student of more than half of the honorees. And so I've known Yael and Lisa for a long time, Jonathan less well and less long, but still it's been really delightful. So thank you for everything over all the years. So I'm going to talk about a project that Yael and I have been working on with Takahiko Yoshida from Tokyo. And this was originally, we sort of had this idea. Yael had been having conversations with each of us and said, oh, I think we should sit down and maybe we can write a 6-hour paper and this will be, and this will be great. That was, I think, in April of 2019. So we're not quite, we're still under 6 years, but we're almost, it's been almost done for a couple of years now. Now it's really almost done. Anyway, so that means, so it should be up on the archive within the next couple of years at least. It still is a 6-hour paper. Well, it got more interesting than we realized. But anyway, so yeah, I'm going to tell you a little bit about that. I'll define all of the terms that are in the title and tell you a little bit about them. So okay, and actually before I didn't realize that the sort of the cultural norm was board talks, and I'm really disappointed because for the first decade of my career, I gave board talks whenever I could, even when everybody else still had slides, and now I have slides, and it was, seriously, Monday night, I thought about trying to switch it to a board talk, but there's a few pictures I want to show you that are on my tablet. So anyway, I'm going to use the board for one thing. I'm going to say, so sort of global assumption, I'm going to be working with Lagrangian fibrations, so M will always be a compact symplectic manifold, and this will be a Lagrangian fibration that is a locally trivial fiber bundle whose fibers are Lagrangian submanifolds. And also, I'll make just a quick remark is that a lot the motivation for study, these are objects that have been studied a lot by a number of different people. A lot of the motivation comes from completely integrable systems. It's a little bit disingenuous to talk about them as completely integrable systems because usually if you have a completely integrable system on a compact manifold, the fibration, you usually have some singular fibers, and I'm not dealing with singular fibers. I'm only dealing with regular Lagrangian fibrations, i.e. actual fibrations. One example that I quite like is the Kodaira-Thurston manifold, so the T2 bundle over the 2 torus. So just to convince you that the class of such examples is not empty. Anyway, so okay, so I'm going to start off by a little bit of background on geometric quantization, which after I got this ready, I realized is not actually necessary for the rest of the talk. Oh, Eugene, yeah. Sorry? Yes, yeah. Assume the fibers are connected. I'm just thinking, yeah, the fibers are all tori. So I'm going to start off by talking a little bit about geometric quantization because I work in geometric quantization. After I prepared the talk, I realized that it's not actually necessary to understand the rest of it, but there's enough, I've seen enough students and things in the audience maybe would like to know a little bit, and I don't know, apparently I can't give a talk without a quick introduction to geometric quantization at the beginning. So if you don't understand anything in the next 6 minutes, then don't worry about it because it won't really affect the rest of it. I was going to say, Ethan, I'm sorry that you didn't get to go after me because you tried to do this, but you had about 1/8 of the time that I do. So anyway, so geometric quantization, very broadly, this is going to be very broad stroke, so I apologize if I offend any people who actually work in quantization. But quantization, we like to use physics language, is a way of going from a classical mechanical system to a quantum mechanical system. And it's sort of the basic idea is what we call canonical quantization in physics, where your classical mechanical system is classical phase space R2n, your position and momentum space, and your quantum mechanical sort of space of quantum mechanical wave functions is just L2 of Rn. So elements here are like your wave functions, and you do all this sort of fancy quantum mechanics stuff that I learned in undergrad and have long since forgotten. More generally, we think of a symplectic manifold as a sort of generalization of a classical mechanical phase space. And then we want to associate to that some sort of Hilbert space, which I'm going to denote by Q of M. And there's a whole bunch of axioms and a whole bunch of things that I'm not going to get into. This is just sort of the broad strokes. In geometric quantization, the way that and I guess I'll say, so really a lot of the time in quantization, the thing that's interesting is actually the operators on this space. And I'm going to ignore all of that. We're just talking about constructing the actual space. In geometric quantization, we construct Q of M from sections of a line bundle, of a complex line bundle. And so one of the main ingredients in geometric quantization is what we call a pre-quantization line bundle, which is a complex line bundle with a connection whose curvature is the symplectic form. So that's when we say a pre-quantization line bundle, we mean a line bundle with connection whose curvature is the symplectic form. And that requires a sort of an integrality condition on omega. Not every manifold is pre-quantizable, but but as long as you have that, then, well, yeah, that's what this condition means. And then, like I said, so our Hilbert space that we're constructing is the space of it's sections of this line bundle. And now there's some subtleties. And the first one is essentially, sort of naively, very naively, if you look at canonical quantization, you say, okay, my classical phase space, I have two n variables, positions and momenta. My quantum mechanical system only depends on half of those variables. Usually, your sort of functions of your position variables. And then in a more abstract symplectic manifold, you say, okay, well, I have two n dimensions here. Which are the variables that I'm interested in? And so the way that geometric quantization deals with that is what's called a polarization, which is, roughly speaking, a choice of half the variables. And again, I'm not going to tell you the general definition of the general theory, but the two main kinds of things that people are interested in are a Kähler polarization, what's called a Kähler polarization, which is given by a complex structure on M. And in that case, then that makes L into a holomorphic line bundle, and then we take our quantum space to be the space of holomorphic sections of the line bundle. The other sort of less popular, but still somewhat popular, still sort of done type of polarization is called a real polarization, which is a little bit more complicated. Whoops, that is not what I wanted to do. There we go. So this is given by a foliation of M by Lagrangian submanifolds. And in this case, so if you sort of imagine if you have your manifold that looks something like this, then maybe we'll take kind of sort of if you imagine the cylinder sort of foliated by circles, something like that. And then we say, okay, then what we want to do is we want to define the quantization to be the space of sections of L that are covariant constant in directions tangent to the leaves of this foliation. So in this, I guess, so in this case, your choice of half the variables is sort of like your variables are the ones along the leaf instead of the ones going the other way around, or the other way. Functions are sort of half of the variables. Now, there's some subtleties in that these sections generally don't exist over the entire manifold, because if you pick one leaf, if you have a loop in the leaf, if you parallel transport along this leaf, that determines the value of your section. And then if you come back to where you started and you get something different, then you can't have a continuous thing defined on the entire set. And so there's a leaf on can't talk and write at the same time. A leaf on which there exists such a section is called Bohr-Sommerfeld leaf. And the set of Bohr-Sommerfeld leaves is typically sort of discrete, sort of like integer values of height or something like that. And then roughly speaking, there's various different approaches to doing this, but the thing that you end up with is roughly that the dimension of the real quantization is equal to the number of Bohr-Sommerfeld fibers. And I mean, essentially, if you don't have that, then you're doing real quantization wrong. So there, that's my very rapid introduction. And so this is sort of like Eugene's TLDR, the summary. Oh, I didn't leave myself enough room here. Come on, there. So if you don't remember anything else, so geometric quantization is determined by sections of a pre-quantization line bundle. Kähler quantization is holomorphic sections. Real quantization comes from Bohr-Sommerfeld fibers. Okay, so with that brief background, I'll say, so our main upstairs, our main theorem, which we called the main upstairs theorem because it had to do, I guess upstairs has to do with stuff happening up here, downstairs is stuff happening down on B, which I'll say more about later. So our main upstairs theorem, if you have a compact symplectic manifold with a Lagrangian fibration, pre-quantization line bundle, then the Riemann-Roch number of M is equal to the number of Bohr-Sommerfeld fibers of this pre-quantization. And so just a reminder, so the Riemann-Roch, the Riemann-Roch number of M is the integral of this sort of cohomology class, e to omega, the Chern class times the Todd class. And if M is a complex manifold, then and if M is a complex manifold and then satisfies some sort of vanishing conditions, this actually gives you the dimension of the space of holomorphic sections. And if M is not compact, or if this other thing doesn't happen, then there's some other sort of fancier recipes that you can look at, Dirac-Dobel quantization, things like that. So sort of morally speaking, this tells you the dimension of your complex, of some sort of complex quantization. So sort of morally speaking, that's what this is. And then the number of Bohr-Sommerfeld fibers, I said a minute ago, that is the dimension of the real quantization. And so this theorem is, you think of it as a sort of independence of polarization result. Oh, I forgot to say that about geometric quantization. If you have one manifold and you have sort of two different polarizations, then you can ask, okay, how much does the resulting quantization depend on that choice of polarization? So this question of independence of polarization is something that gets a lot of attention in geometric quantization. So this is a sort of an independence of polarization result. So in principle, this result is known. It's given in a paper by Fujita, Furuta, and Yoshida, and they attribute it to a paper to Anderson. And we dug out Anderson's paper and read through it, and it's not quite exactly this result, and the proof is kind of hard to follow. And so we said, okay, we'll give a straightforward, simple, direct proof of this in the case of Lagrangian, compact Lagrangian fibrations. And so that's what I'm going to do. I'm going to say something about sort of the structure, some of the structures of Lagrangian fibrations and how they interact with quantization, and something about this proof that we're giving. How am I doing here? I'm sorry?
In particular, it's independent of the connection also.
Yes.
Right. So it's not only independent of the choice of polarization, but it's even independent of because the right-hand side is it's even independent of the choice of connection.
Right. That's right. And in fact, I mean, so towards the end, I'll say, so in fact, it's yeah, if you have, that's right, yeah.
Which is not obvious if you have a non-simple relation.
Right, right. That's a good point, yeah. Yeah. I would, so this is an interesting question. Yeah, what happens if you have sort of singular polarizations? I would expect something like this to be true, but I don't have, so I mean, yeah, this question of.
There's this result we not have.
Well, so yeah, that's yeah. Well, that's a little bit different. That's more complicated. But yeah, so the question of, I don't know, this question of like what you do with singular real polarizations is one that's definitely been around. People are talking about saying somebody should do it, but nobody has yet. Right, right. Okay, so a few words about Lagrangian fibrations. Like I said, they've been studied a lot. Some Doistermaat, Zoom, Symington, Sepe are some names that I'm aware of. I'm sure there's others. So one of the big theorems is, and the geometry of a Lagrangian fibration turns out to be quite rigid. So one of the main theorems is known as the Arnold-Liouville theorem, comes from mechanics, says that the connected components of the fibers of a Lagrangian fibration are tori. And in fact, we sort of sort of semi-locally symplectomorphic to U cross Tn. So let's say I have an open set in U, and I look at the preimage of that in the fibration. Then, okay, so let's say U is diffeomorphic to some open set in Rn, and then the sort of the piece upstairs is symplectomorphic to just this open set cross Tn, where the symplectic form is standard. So if I have coordinates x on Rn and t on the torus, then the symplectic form is just the standard symplectic form. And these sort of x, t coordinates are called action angle coordinates. And I guess I'll mention sort of in the proof of the Arnold-Liouville theorem, you can construct these action coordinates by if you take a primitive of the symplectic form and you integrate it over cycles in the tori. So if you take a torus fiber and you take sort of a homology basis for the basis of homology cycles for the H1 in the torus, then if you can define your sort of jth action coordinate as just the integral of this primitive over these various cycles. And then you look at how that changes as you change your base point, and that gives you action coordinates. And yeah, so now, okay, so you can say, okay, so given such a thing, how much is that determined? Well, okay, so action coordinates computed in this way are they're defined up to, well, okay, if I choose a different primitive of my symplectic form, that's going to sort of add a global constant to all of my action coordinates, so that's sort of a shift. Or I could choose a different homology basis for the fibers, so that will give me sort of a different set of coordinates, but they'll differ by an action of an element of GLNZ. Sort of to go from one set basis to another. Okay, so now in our paper we phrase this in terms of what we call Arnold-Liouville charts, which is essentially just formalizing this definition. And I just realized that maybe I should have. And this is a copy of the previous diagram, so I'm sorry. Oops, that's not a cross. That's contained in. So if we have x1 through xn, and we have so an Arnold-Liouville chart. Oh my God, what is going on here? Sorry, this is the problem with touch screens. Don't know how to get rid of. Oh, I bet I could get rid of that. Anyway, I'll figure that out for the next time I give a talk. Okay, so an Arnold-Liouville chart is essentially this type of structure. So a diffeomorphism from an open set in B to an open set in Rn that lifts to a symplectomorphism from the inverse image of the open set to the omega cross Tn. And so we phrase the Arnold-Liouville theorem by saying that every proper Lagrangian fibration with connected fibers can be covered by Arnold-Liouville charts. And okay, so then okay, so now if we say, okay, if we have the transition between two of these charts, those maps, mentioned sort of the rigidity of the geometry, transition maps between the two of those charts have a very specific form. So if I take xt goes to, so on the base, it looks like, okay, I'm not gonna try and write at the same time, sorry. So A is an element of GLNZ, B is an element of Rn, and G is just some function that we don't care about. That should be a transpose. Okay, so what this says is that if I have the map between two of these sort of Arnold-Liouville models, the base transformation looks like an integral affine transformation. And then upstairs, it's sort of the inverse transpose of the same transformation plus some function of the base coordinates that don't necessarily. There's a little bit more you can say about that, but I'm going to not. But it's not going to matter. Whoops, sorry. This is supposed to be. This is supposed to be down here. That makes more sense. There we go. And So this equips B with an integral affine structure because we can, by Arnold-Liouville, we can cover the whole thing by these Arnold-Liouville charts, and then the transition maps between two charts have this form. In particular, on the base, they're integral affine transformations. And so that makes B into an integral affine manifold. And I guess I'm not, so I learned this, I don't know where it's from originally. I learned it from Sepe and Symington. Sepe has a result that B is the base of an integral, B is the base of a Lagrangian fibration if and only if it has an integral affine structure. Yes, right. I learned it from your paper. So, okay, so now so that's just for Lagrangian fibrations. Now, if we have a pre-quantization in the picture as well, we get a little bit more structure. So suppose we have a Lagrangian fibration, pre-quantization line bundle, which again is a complex line bundle with connection whose curvature is omega. Then we have sort of a similar kind of local result, which I'm afraid, again, going to phrase in terms of these charts, which we call enhanced Arnold-Liouville charts. So we take all of the stuff and put enhanced in front of it. Enhanced is we've got a quantization going on. So same picture that I had for the Arnold-Liouville chart. I have sort of an open set of my base, lift it to a sort of neighborhood of a fiber upstairs, and then I'm going to look at the bundle restricted to that open set. So similarly, that's going to be isomorphic to my open set cross some, well, just cross C. So, but this, right. So the point here, right? So I mean, the important thing here is, so I have a standard form for the symplectic form, and then the point I can put the connection into. Oh, for God's sake. Okay. Sorry about this, everybody. I can put the connection in a standard form. The connection is d minus 2 pi I sum xj dtj. So we'll call that an enhanced Arnold-Liouville model. So essentially, I've sort of lifted my Arnold-Liouville, sort of so Arnold-Liouville gives me a standard picture local model for the fibration. This gives me a standard local model for the line bundle along with the connection. So the connection has this sort of specific, nice canonical form. And then, so maybe called the enhanced Arnold-Liouville theorem is that essentially every pre-quantized proper Lagrangian fibration with connected fibers is locally isomorphic to an enhanced Arnold-Liouville model. So essentially you can always find, you can always trivialize your bundle over one of these neighborhoods in such a way that the connection has this particular form. And I had a note about the proof, but I don't think it's that important, and in the interest of time, I'm going to skip ahead. Basically, it's a computation of the coordinates. You compute holonomy, and then you sort of adjust things slightly. And then, so we have a similar, so I said before, we had Arnold-Liouville models, changes between them have a certain form. Then we have a similar kind of result for the enhanced case. So the isomorphisms of enhanced Arnold-Liouville models have the same sort of form. So again, the first two coordinates looks exactly the same, except so the difference here is that now instead of just an integral affine transformation here, we actually have a stronger condition where the translation of that is also an integer. And so we call a map of that form an integral affine map. So not just integral, but integral or extra integral or something like that. And this equips B with sort of what we call an integral affine structure, like an integral affine structure. But again, the translation sort of essentially it's the same thing. We're not just the sort of the not rotations, but not just the multiplications, but also the translations are integer valued. Yes. So one of the things that we get out of that is what we call the set of integral points in B. So if I take some integral affine chart map to to Rn, then I can take Zn sitting inside Rn. And if I pull that back by this chart, then I get sort of essentially something that looks kind of lattice-like in B, locally lattice-like. And then the point is because the transitions between these different charts have essentially preserved. I guess, yeah. So you can express one of these integral affine maps as there's maps that preserve the lattice Zn sitting inside Rn. And so because of that, this gives us sort of a well-defined notion of integral points in the base B. And so after that, let's see. Right. So we say that we can show that a pre-quantization over a Lagrangian fibration determines an integral affine structure on the base B, such that the integral points of coming in the integral affine structure are exactly the Bohr-Sommerfeld points in the pre-quantization. So remember the Bohr-Sommerfeld points are points where essentially the holonomy of the connection is trivial around in all directions of the fiber. And let's see, I had this written down as it's obvious, and now I'm just thinking, right. Well, yeah. So essentially, so that was part of the. So the holonomy of the connection is essentially e to the 2 pi I times the value of the action coordinate, and so the holonomy is trivial precisely when the action coordinates are integers. And so essentially, what's going on here is remember we said that the action coordinates are determined by integrating a primitive of the symplectic form over the cycles. There's not really a natural choice of primitive. If you have a pre-quantization, then if you take the one form representing the connection in any trivialization, that will be a primitive of the symplectic form. So it sort of gives you a natural choice of which primitive to use. If you use that to define your action coordinates, then the action coordinates will have integers at precisely the Bohr-Sommerfeld points, and so that defines your set of integral points in B. So that's how that. So it sort of lets you nail down sort of the translations so that you know which ones are the integers. Okay. All right. So hang on. So the promised short, sweet, simple proof of the main upstairs theorem, which I should have written down so we had it for reference, but again, we're saying Riemann-Roch number is equal to the number of Bohr-Sommerfeld points. So the Riemann-Roch number is, well, purple and went black. So that is e to the omega times Todd of Tm. Right, so the first step is that we show that the Todd class the Todd class is 1, so this just works out to be integral of e to the omega. And so if you pick out the right dimension, you get 1 over n factorial times omega to the n. And so that's just the Liouville measure on M, so you just get the volume of M. And say, okay, well then, now if I push forward the Liouville measure to the base, then that I can show that that's just the volume of B. So this is push forward. And now, okay, so as mentioned before, we have an integral affine structure on the base B, and such that the Bohr-Sommerfeld points are exactly the integer points coming from this integral affine structure. And so, all right, so obviously the number of integer points is equal to the volume. And so that is equal to the number of Bohr-Sommerfeld, and there we go. Or so this is the result above. All right, cool. Now, so yeah, some of you have figured out where I'm going with this. The problem was that this obvious result was surprisingly not obvious. We were sort of writing up this proof. We had, okay, this step, this step, this step, this step, okay, volume thing, and sort of, this is obviously true, and then let's write this down, okay, and we were trying to write down sort of a proof of this obvious fact, and we couldn't do it over the course of for a couple of days. I think we were sitting in Toronto, sitting around Yale's office, and we're like, okay, what about this? What about this? What about some sort of like pick thing? And I don't know, all these different things, and it was sort of, well, again, not obvious. And so we said, okay, let's think about this a little bit more. And I think we even wrote to Bill and so like, do you know this result? Have you heard about a thing? And so my next section is a surprising theorem. Not because it's the theorem itself is surprising, because the statement is obviously true, but because it was surprisingly not easy to prove. And so for a little while, we sort of toyed with the idea of flipping the logic around. We said, well, okay, our main upstairs theorem is actually a theorem in Anderson. That was before we looked at it too closely. And we said, okay, well, we know that that's true. And so we could sort of work backwards and say, well, because that's true, therefore, this statement, which is just in integral affine geometry, which has nothing to do with quantization at all, we can use that to prove this. But that's morally wrong. That's inappropriate. It just felt wrong. And so we were briefly considered titling our paper an inappropriate proof using geometric quantization of a simple fact from integral affine geometry. Fortunately for the typesetters, we did find a proof, but it was sort of more, like I said, it was more complicated than expected. So Takahiko sort of came up with this proof. He said it was, and I guess some of these techniques are maybe well known in mirror symmetry or Lagrangian Floer theory or something like that, neither of which I know anything about, so I can't say. We were not able to find a proof sort of explicitly written down in the literature. There's some sort of similar techniques used in a few places. So, but anyway, so I want to say something about it, and I don't know. Apparently, I am unable to work out timing because I was worried that I was going to run out of time, and now I'm going to run out of material. But anyway. That's right, especially the one that's right before lunch. So now watch, after all this, I'm gonna go over the end. Okay, so I'm gonna say a little bit about some of the structures that we get out of these constructions. So an integral affine structure on a manifold B, yeah, that's about all I was going to say. So this is a proof of a fact like I said, on the surface has nothing to do with quantization, just purely integral affine geometry. So we have an integral affine structure on a manifold B. That determines a lattice in the tangent bundle. So if we take either one, both. So if you take essentially, so if you take an affine chart and you take the pre-image of, if you take the tangent bundle of Rn, which just looks like Rn, and you take Zn sitting inside that, and then you pull that back by phi, then that gives you a, let's see, or the derivative of phi, I guess I should be doing this at a point there. So at any point, right, so you take the derivative of a chart, of an integral affine chart, and then take the pre-image of Zn under that. That gives you a lattice in the tangent space, and then that gives you a lattice bundle. And then that, that's well defined because the transitions, the integral affine map, the transition maps between these are in GLNZ. If you write it in local coordinates, you can just write it as sort of m times d dxj, sort of integer multiples of your sort of basis vectors. And so if you have an integral affine structure on B, that gives you another sort of structure, which we call the affine lattice, which, I don't know, it took me a long time to sort of get much intuition for this. Yael was like, oh yes, we have this thing, this is great. And I'm like, what the heck are we talking about? Essentially what we do is you take, so it's the same sort of idea, you have an integral affine chart, whoops, and we look at the pre-image of Zn under, or sorry, this is, again, we look at the derivative and we look at the pre-image of Zn under the map phi plus phi star. Yeah, the linear approximation. I've never quite, that never made sort of intuitive sense to me. But or if you like me, like doing everything in local coordinates, it's essentially in local coordinates, it's just mj minus xj ddxj. And so let's see. Okay, let's see if this works. So if we kind of hello, there we go. So if we say, if we sort of imagine, okay, so on this side we have our, sort of here we are in Rn, here's the tangent bundle of Rn, and then sort of we just have the Zn in every fiber, and then we pull all of that back under sort of using these things. Then, so the purple here is meant to be the integer lattice, which is just Zn, and then the blue is the affine lattice. So it's kind of like lines of constant slope -1 in these fibers. And so notice that it intersects so the intersection of, let's see, so let's call the lattice lambda, and the affine lattice, let's just call lambda affine. So the affine lattice intersects the integer lattice precisely above the integer points in the base. Because, I mean, however you want to look at it, this way, that's where the xj's are going to be integers. Okay. So now if we take the tangent bundle and mod out by this lattice, then we get a torus bundle. And I actually, Yael hasn't seen this picture yet. I don't know. I think this is kind of a neat picture. So let's say, so here's B, and if I imagine kind of taking this picture and kind of rolling it up along the purple one, then I can imagine getting sort of a little sort of torus tube sitting above B here. And it's kind of, so now, okay, so then the purple lattice will go to the zero section of the zero section of this torus here, and then the affine lattice, the blue section, gives rise to another section of the torus bundle that sort of, you can sort of imagine it sort of wraps around the torus like this. And it's going to intersect the zero section precisely above the integer points in B. So, okay, so that's what I just said. The affine lattice gives rise to another section that intersects the zero section above the integer points. And so, okay, so we can compute so the number of these intersection, sorry, the number of these integer points is just the intersection number of the image of the blue section with the purple section. So, I mean, you can show that the intersections are all transverse and they all have the same orientation. That just sort of follows from from the picture, right? So, okay. So then we should, okay, so then, yeah, proposition, there's a unique closed end form on this torus bundle. That's the Poincare dual of the section Z naught. And actually, if we say if coordinates, if I have x coordinates on the base and then y coordinates in the fiber, which will be mod 1, then this really is just dy1 wedge up to dyn. And the y1, yn are maybe not necessarily uniquely defined, but their wedge product is. And then you can show that that's the Poincare dual of Z naught, which I won't say something about how we do that, which also there's some interesting things there, but I realize it's been a while. And then, okay, if we pull back this form by S, we just get dx1, just the sort of standard volume form on B. And so if we compute so this is the intersection number with Z naught, which is just the integral over SB of dyn, which if we pull that all back downstairs, then we just get the volume of B, which is I don't know, I think it's cute. And again, we have not come up with an easier way to see this obvious fact, but it's still sort of cute. So okay, I want to one corollary to this, so something that Jonathan was mentioning is that if we have, so yeah, a corollary to this, maybe not so much the theorem, but a corollary to part of the proof, the simple direct proof, is that if we have different real polarizations on the same manifold, they'll give you the same number of Bohr-Sommerfeld fibers or the same dimension of quantization, right? Because somewhere along the way we had a result that said that the number of Bohr-Sommerfeld fibers was the volume of B, which was equal to the volume of M. So if I have sort of two different Lagrangian fibrations, with different bases perhaps, but the number of those, the number of Bohr-Sommerfeld points in each of those is going to be equal to the volume of M, so it's got to be the same. And so one sort of neat, sort of cute example of this is something that my honors student Zoe McIntyre worked out sort of a number of years ago, but I'm maybe finally going to actually write this up for publication. It's sort of cute. Different polarizations on the Kodaira-Thurston manifold. So just briefly, so if you are familiar, Kodaira-Thurston manifold is, I said before, you can realize it as the 2 torus bundle over the 2 torus. You can write it as the quotient of R4 by a group of affine transformations, or integral affine transformations. And the exact form of them is not super important. So if it's confusing, you don't have to worry about the details. Basically, I mean, essentially, it says that 3 of the coordinates are just all the coordinates are just mod 1, and then if you shift by 1, and if you sort of go around once in the x direction, then something funny happens in the u coordinate. So you get sort of this fibration with some monodromy, and then so this is standard symplectic form, and so anyway, Zoe and I were looking at, you can realize this as a Lagrangian torus fibration in several different ways. So one of them is you project to these coordinates, one you project to those coordinates. What's interesting about this is that, so this projection has monodromy as a torus fibration. This one doesn't. And then if you sort of go through and sort of essentially run this machinery of quantization, figure out action coordinates and look at interaction coordinates and things, you get sort of these cute pictures. So this one, you have sort of this is what your sort of Bohr-Sommerfeld spectrum looks like, or your Bohr-Sommerfeld points in the torus, right? The rectangle identifies as the torus, and I mean you can if you sort of trace it around, you can see the monodromy coming in this picture. If you go around it once, you get something like that. Whereas if you do it on This one, it's just very boring and very straightforward. But again, the number of, in each one of these, the number of points is just, oh, right, well, so this is I've scaled my symplectic form so that you can actually see something. And in each one of these, the number of points is just k squared, of course, which is just the volume. So, all right, I think that's it. I could, yeah, there's a few more structures I could tell you about, but as we said, nobody complained that the last speaker before lunch finishes 5 minutes early, so I'll stop there.